Hello students, so today we are going to discuss about hard and soft water. So we use water in many different ways and the type of water changes with the use. As for example, for drinking purpose we use mineral water. It is specifically called mineral water because some minerals are dissolved in it and these minerals are necessary for our body. We obtain different type of nutritions from different type of sources. Some of the nutritions we can obtain it from food, some of the nutritions can be obtained from water, and we can obtain vitamin D, actually energy for vitamin D, from sunlight. So water provides some of the important minerals required by our body. So that's why we use mineral water. So basically it is not pure water, it has some salts dissolved in it, and these salts are our requirement. So if we remove all the salts from the water, then you will have distilled water. It is pure form of water. And then we can use little bit impure water for our daily needs, that means for washing purpose. So we have multiple different type of waters, but we cannot use water if amount of salt is comparatively higher. So when droplets of water produces in cloud, it is purest form of water, naturally occurring source. So it is purest form of water. When it comes to the atmosphere, when it passes through the atmosphere to the land, some of the gases will dissolve in it. So it is almost pure when it reaches to the earth. And then when it comes in contact with earth, it will start flowing on the surface of earth, and many type of salts will dissolve in it. So that's why it is not pure form of water. And if water contains specifically calcium and magnesium, chloride, sulfate and hydrocarbonate, then it is called hard water. And hard water is almost useless. Hard water do not give foam with soap. That means soap molecules are basically, it contains two different type of parts, hydrophobic and hydrophilic. This is the molecular formula of soap, C17H35 COO So C17H35, it is hydrocarbon chain. So we can simply represent it with this type of zigzag line, and at the end of this line we have COO minus ion, and with this minus ion Na plus ion is attached via ionic bond. So we have a COO minus and Na plus attached with it. So here we have ionic bonding. So when we dissolve soap into the water, Na plus and COO minus will separate out because of ionization. So they will separate out, and we have a long chain of hydrocarbon attached with COO minus negative ion. So now long hydrocarbon chain will act as hydrophobic part. Hydrophobic part, that means it will repel the water, because this hydrocarbon part is non-polar. So usually non-polar molecules feels attraction towards the non-polar molecules, and polar molecule feels attraction towards the polar. So this COO minus part is called head, and it is polar, and this tail or C17H35 or hydrocarbon chain, it is non-polar. So as mentioned, water molecules are polar molecules, so it will feel attraction towards the head of the ion. This is called stearate ion. When Na plus is removed, then it is called stearate ion, and this formula is for sodium stearate. So towards the polar head, water molecules will feel attraction, and towards the non-polar tail, oil droplets, grease droplets or dust or stains will feel attraction towards the tail, because all of these particles are non-polar. That's why non-polar attracts non-polar. So usually oil and water do not attract each other, and that's why if we have oil, we cannot wash it with only water because they do not feel attraction. But with the help of soap, we can easily remove it. And reason behind that is soap behave as link between water molecules and oil droplets. So because it feels attraction towards the both of them. So that's why we can wash it off. So what is the problem with hard water? So when stearate ions are present in hard water contains Ca2 plus and Mg2 plus impurities. So these type of ions will feel attraction towards the negative ion, and it will produce calcium or magnesium salt of the stearate ion. And now these bonds are permanent. That means with calcium or magnesium, these ions do not dissociate in water. So if heads are permanently attached with ions, then water molecules can't feel attraction towards them. And that's why these molecules are not able to attach with water, and that's why they are useless as mentioned in this reaction. Second problem with hard water is we cannot use hard water for industrial purpose as well, because when hard water passes through the pipes or when we use it in boilers, usually salts, excess quantity of salts present in the hard water will start depositing on the surface of inner walls of pipes or inside the boilers. Eventually it will create thick layer of the salts, and because of this thick layer, transformation of heat decreases, because metals are good insulator good conductors of heat, but salts are not. So salt layer will decrease the efficiency of boilers, and it will block the pipes. So as we let it pass through the pipes, more and more salt will deposit inside the pipes. Eventually pipes will be blocked, and it will lead to create pressure, and finally it will blast. So these type of industrial accidents do happen because of hard water. So hard water is useless for our regular household uses or even for industrial uses. So that's why we need to remove this hardness from the water to make it usable. So usually these type of hardness have two different types, temporary and permanent. So as the name suggests, temporary hardness, they will be easy to remove, and permanent hardness, they are comparatively hard to remove. So first let's discuss about removal of temporary hardness. If water contains specifically hydrogen carbonate salts of magnesium and calcium, then it is called temporary hardness, because these salts are easy to remove. So first step, we can boil them. So when we boil them, magnesium and calcium hydrogen carbonate changes into magnesium hydroxide and calcium carbonate respectively. Both of these compounds are insoluble in water. So simply these salts will precipitate, and then we can simply filter the water and you will get soft water. Second one is Clark's method. Basically it is the same method just like boiling, but instead of providing energy we are adding some chemicals. So by addition of calcium hydroxide or lime, we can create calcium carbonate or magnesium hydroxide just like boiling. So as we discussed already, calcium carbonate and magnesium hydroxides are insoluble salts, so they will precipitate out, and with the simple filtration we can remove these salts. So we have to calculate the quantity of lime, because if we add more quantity of lime, then it will add salts of calcium in it, because lime, it is calcium hydroxide. So basically we need to remove impurities of calcium, and we are adding calcium. So that's why we have to properly calculate the amount of calcium hydroxide. So that's why it won't add into the impurities. Then we have second type of hardness, permanent hardness. It is hard to remove, and that's why we need to use some more chemically useful methods. So all of these methods basically has exchange of ion. That means we will exchange or change calcium and magnesium from the water, and instead we will add some simpler ions so that hardness can be reduced. So first is with washing soda or sodium carbonate. When we add sodium carbonate, then it simply replaces magnesium or calcium from the water, and it will provide sodium instead. So if we have chloride or sulfate, impurities of calcium and magnesium, then with the addition of washing soda or sodium carbonate, simply M will be replaced with Na, and Na will be replaced with M, where M represents Mg or Ca. So MgCO3 or CaCO3. Both of them are insoluble in water, so it will precipitate out and you will get NaCl or Na2SO4. So these salts won't create hardness in water because specifically Mg and Ca are responsible for the hardness. In second method, we will use sodium hexametaphosphate or commonly known as calgon. So this chemical will turn calcium or magnesium salt into complex compound, and this complex compound will trap or they will be permanently bonded with calcium or magnesium. That's why they are not able to connect with water, soap molecules, and hardness will be removed. So sodium hexametaphosphate will ionize, it will remove 2 of the sodium and you will left with Na4P6O18 2 minus. Now Mg and Ca will combine with this ion and it will turn into this type of complex compound. Here our metals are present here. So now these metals are permanently bonded with this molecule or complex compound, so they won't be able to remove or release from this molecule, and that's why they won't create hardness. So they are still present in water, but they won't hinder in our reactions now. Now next two methods are comparatively important. First one is ion exchange method. So in this method we will use zeolite or permutate. Because of that, this method is also known as zeolite or permutate method. Now for the simplification, we will represent zeolite as NaZ because AlSiO4. It is common formula for zeolite and we have sodium attached with it, so it is called sodium aluminosilicate or sodium aluminium silicate. So we will represent zeolite as Z. So simply we can write it as NaZ. So when we add NaZ into the water, hard water, it simply replaces the Ca or Mg with sodium. That's why it is known as ion exchange. It will provide sodium and it will take calcium or magnesium from the solution. So after the reaction, we will get Mz2 and Na plus ions will be dissolved in water. Now, like previous method, this compound Mz2, it is not useless. We can recharge it and then we can use it again. So when we pass this Mz2 compound from the salt water or sodium chloride water, we can again regenerate it and we can again use it for further purification of water. So when we treat Mz2 with NaCl water, it simply again exchanges our metal ions with sodium ions and you will get NaZ. That means sodium aluminium silicate and MCl2 will be present in solution. So we can use this compound to remove hardness again. And next method is even more efficient. We have synthetic resin method. So in synthetic resin method, we use large organic molecule with SO3H group. So basically it is like soap molecules. As mentioned in soap, we have long hydrocarbon chain with COONA group at the end. In this case, instead of COONA, we have SO3H group and we have long hydrocarbon chain. So it will exchange the ions from the solution just like the previous method. But in this method we have two different type of salts or resins which can remove two different type of ions, and namely positive and negative ion. That means using this method we can even remove negative ions as well, and that's why this is more efficient method. So first of all, we will represent this resin as RSO3H for simplification. So when we add it into salt solution, NaCl solution, simply SO3H group will be replaced with sodium. So you will get RNA. So this RNA will replace sodium or magnesium from the water as mentioned in this reaction. RNA plus M2 2 plus will produce R2M. That means our salts are removed from the solution and Na plus ions will be added in it. And just like the zeolite, we can regenerate by adding this R2M into the salt solution. Now if our requirement is for pure demineralized or deionized water, then we can use this ion exchange method or resin method. So instead of RNA, we will use RH. We will use two different type of resins. First, cation exchange and then anion exchange. So cation exchange, that means our Ca and Mg will be replaced with H plus. That means we are trading H plus to get Ca and Mg out of the water. And similarly, for anion exchange, we are trading OH minus. We will provide water OH minus ions and we will take whatever the negative ions are present as impurity in hard water. So first, we will pass cation exchange from the solution. That means we will pass RH. So our metal will combine with R or resin and it will provide us Mr2 and H plus will be added in the water. That means RH will is able to remove Na plus, Ca2 plus and Mg2 plus from the water. And because of addition of H plus, water will turn acidic. And now in next step we will add anion exchange to remove negative ions from the water. So first RNH2 will be treated with water to provide RNH3OH, just like reaction of ammonia and water. When we add ammonia into the water, then ammonia is base, that's why it will accept H plus and it will turn into NH4 plus. And water is less basic than the ammonia, that means it will act as acid and acid provides H plus. So H plus will be removed from the water molecule and you will left with OH minus. So basically ammonia and water molecule will provide ammonium hydroxide NH4OH. So similar type of reaction occurs here. Instead of 3 hydrogen, we have 2 hydrogen and 1 hydrogen is replaced with R group or resin. And whole reaction is similar just like the ammonia. So now this RNH3OH minus, it will react with negative ions present in the water as impurity and it will replace OH and X with each other. So X minus ions, that means impurity of negative ions, will be removed with resin and resin will provide OH minus ion to the water. Now in first step H plus were added and in second step OH minus are added. So H plus and OH minus will turn into water molecules. So our water is completely free from ions. And now these resins are not useless, we can regenerate them by addition of acid and base respectively. In cation exchange resins we will add diluted acid and in anion exchange resin we will add diluted alkali solutions to regenerate them. So we can use them again for purification.